All right, in this lecture I want to talk a little bit more about even and odd functions. We'll look at some definitions as well as some mathematical formulas and just get a little bit better. Even though we've talked about them before, I want to get a little bit more in depth into what they are and why it's significant. So basically, the Fourier series for functions that are either even or odd or display other kinds of symmetry take on a simpler form and make calculations easier. And so it enables us to eliminate a lot of calculations, as you'll see in your classes on down the road in the curriculum. And they have a pretty specific definition. So I want to say first that a function can be even or odd without being periodic. So it is possible to have an even function that is not periodic or an odd function that is not periodic. Pulse that's of rectangular shape and centered about the origin. That would be an even function, but it would not be periodic because it occurs only once. So when we talk about Fourier series, we're always talking about periodic functions. However, when we talk about even and odd, being periodic is not a requirement for being even or odd. So the definition of an even function is if the function f of x is equal to the function f of minus x for all x. And so the graph of an even function is basically symmetric about the y-axis. A function is odd if f of x is equal to minus f of minus x. In other words, it is both rotated around the y-axis and the x-axis, so it's rotated and flipped. So if f of x was 3, then f of minus 3 would be minus 3. So that's called skew symmetric. So there are some operations, and one thing to keep in mind is that most functions are neither even nor odd. For example, e to the x plus x squared, neither even nor odd for either of those functions. Another thing to keep in mind is there are some rules about multiplication. So if we multiply two even functions together, we end up with an even function. If we multiply two odd functions together, we also end up with an even function because that's a double negative. If we multiply an odd times an even, we end up with an odd. There are some rules about addition as well. For example, if we go and extrapolate this to Fourier series, an even function can only be a sum of even functions. So since the cosine function is even, if we have an even function, its Fourier series will only consist of cosine functions and possibly a constant. Whereas if the function is odd, it can only be realized by summing odd functions. So an odd function would have a Fourier series that would consist of only sines and no constant. So there are some interesting repercussions of even and odd. All right, now another interesting thing is that any function can be written as the sum of an even function and an odd function. So any function h of x can be written as the sum of an even function and an odd function. And we basically can take this equation and invert it, and we get that an even function is 1/2 of h of x plus h of minus x. So let's suppose that your function was, I don't know, trying to think of a non-even or odd function. Let's say we had e to the x. Then basically to find the even part, we would take 1/2 of e to the x plus e to the minus x. And to find the odd part, we would take 1/2 of e to the x minus e to the minus x. So you can find an even part and an odd part if you're given any function. Once again, this does not have to be periodic. This is just a general description for what is even and what is odd. So the Fourier series of an even periodic function consists only of the cosine terms and the initial constant. So first of all, this is written as approximate here because obviously no true sum is going to go all the way to an infinite number of terms. So the Fourier series does approximate the actual mathematical function. In this case, period is 2L. And so instead of the typical cosine omega t, which we see, or cosine of n omega t, which we see in electrical engineering, this is just more of a mathematician's description where we have n pi x over L with 2L being the period. So don't let the constants concern you. Mostly what I want you to get out of this is that for an even function, we have a sum of sinusoids. Now, the Fourier series for an odd periodic function, basically you end up with all of the a coefficients becoming 0. So once again, this integration term is for those of you who had calculus. This is how you actually find the value of the coefficients. If you haven't had calculus, this is just here for the information of those who have. This is not something you need to memorize or be responsible for on an exam, this equation here. Okay, so basically for the odd function, f of x would be, there's no a sub 0, and instead of cosine, you would have sine, and instead of a sub n, you would have b sub n. For whatever reason, the author of this particular set of slides didn't include that actual formula. But once again, it's not that important. These are mostly shown here for your information. All right, so let's get what some important concepts are from the materials we've been over. First of all, it is important and you need to know, so yes, this is something, these are things you'll be responsible for on an exam. So first of all, you'll need to know how to prove that a function is periodic. Secondly, you'll need to be able to find the fundamental frequency of a periodic function, both from a graph and mathematically. Third, given a series, you'll need to be able to plot the amplitude plot and vice versa. Fourth, you'll need to know how to prove that a function is even or odd mathematically or by looking at it or viewing a graph. And finally, you'll need to be able to find the even and odd components of a function that is neither even nor odd. So those are some of the things in addition to what we already covered in the first set of lectures from the week of March 30th on sinusoidal functions in general and ECE. This is the new material that will also be on the last exam. All right, so I've got some slides here and you can access these from the PowerPoint posting on the week of April 6th. But I do have some slides here that show you some examples of kinds of questions that you might see on such an exam. So for the first part, you want to look at these periodic functions and state by inspection of the graph whether the function is even, odd, or neither. Now in this particular lecture, I'm not going to answer the questions for you because I want you to be able to go through, so you can consider these last few slides like an optional homework that will not be graded, but you need to look at the slides and you need to see if you can figure out the answers. In about a week, I will post the answers so that you know whether or not you got them right, but we'll look here briefly. So one thing to comment about the format is that on these graphs, you assume that you can see how it continues on in this direction, so you assume it would continue in the other direction. Basically, this pattern repeats both to the right and to the left. So this would have a continued, if you look, basically it would come down and then it would go across and then down some more. So it's going to, continue this pattern both before and after this one cycle. So they're only showing one cycle here, but know that it continues along the negative and the positive time axis. And since it's periodic, you would need to see from here to here basically repeated both in the forward and in the backward direction. It will not, in this case, it will not flip or reflect. It basically, you would take this guy and put him right here. Same here, this is a pulse train, so you can continue, you can assume that there are more pulses back here and more pulses going in this direction. Just two are illustrated here. Same here, this triangle wave would continue in the negative and in the positive direction. Same here, this would come down, flat, up, just like it does on this side. So it's this pattern from, in this case, 0 to t, that's repeating both to the right and to the left. Same here, this is a series of triangle pulses. And same here, this is a series of unusually shaped weird pulses. Okay, so those were examples of looking at functions and determining if they are even, odd, or neither. Here is another example. You're given this function below, and what you want to do is find the following. You want to find the fundamental frequency. You want to find whether the function is odd, even, or neither. You want to find whether the function is periodic, and you want to find the amplitude spectrum. So remember, you need to look at the definitions. You can't just say, oh, it's odd, or oh, it's even, because you don't have a graph to inspect. So you actually have to go back to the definition. So what was the definition? If it's even, then f of t is equal to f of minus t. So plug in minus t everywhere you have a t, set it equal to f of t, and see if it's true. As far as odd, that would satisfy that minus f of minus t. So plug in minus t, make it all negative, set it equal to f of t, and see if that is true. When a function is periodic, if you remember how to prove that, basically you take the value at f of t, and then you take the value at f of t plus 2 pi, or plus 2n pi, plus or minus 2n pi, and you prove that the function is the same for an integer multiple of a 2 pi cycle. All right, here are some examples regarding even and odd. So basically you want to state whether the functions in their functional form below are even or odd or neither. And then if they're neither, you want to find the even and odd components of the functions. We've showed those formulas today, earlier in this lecture. And so you can scroll back through the PowerPoint slides to find the formulas that you use to determine whether the function is even or odd. And if it's neither, then you can use the equations for the even and odd functions given a function in order to generate those. So these are some examples, as I said, that I want you to work through, and I'll provide answers to these next week. But I think it's really important, if you want practice for the exam, that you try to work through them on your own first. And that pretty much concludes everything that we're going to discuss on sinusoidal functions that you will be responsible for on your third exam. So there's not a lot of material here. So what have we talked about? We've talked about sinusoidal functions. We've talked about how in AC circuits we're often taking a function in the time domain that's a cosine function with a magnitude and a phase shift. We're converting that to the phasor domain. We're doing any math that's required to be done, and we're often converting it back to the time domain. So we talked about that. We once again presented Euler's formula, where you convert from rectangular to polar and polar to rectangular in the complex plane. We then talked about sinusoids in general and some definitions. We talked about even and odd. We talked about what is meant by a periodic function, and we talked about the Fourier transform, the Fourier series. So you will get more work to reinforce the Fourier series on your project, project 7. Project 7 reinforces building a Fourier series using MATLAB, and so you'll be able to see how that works in real time. I'll make one more video this week that discusses Project 7, and because the commands that you need for Project 7, some of them are plots, and so you need to go back to the plotting lecture, and then you're going to have to be able to use arrays to construct the function that you're building and plot it. And so there's a little bit of interesting trickery there on keeping track of where your indices are. So anyway, this pretty much concludes, as I said, the lectures on sinusoidal functions, and now it's up to you to work the problems and see if you have any questions or issues.